Okay, so in today's session, we will be reviewing and we'll be covering solution and solution concentration calculations. This is especially important as it ties into and is foundational material for later classes that you'll take as part of the allied health curriculum on formulation, etc. Okay, so let's talk about different ways of expressing solution concentration. And all of these measures of concentration are often expressed in terms of solute, solvent, and solution. The first type of solution concentration measurement that we'll look at is percent concentration or percent by mass. Now, it is a unitless value. The units in grams cancel. And mass percent or percent by mass is formally defined for a solution as the mass of solute, which is the minor component, over the mass of solution, which is the total mass. The mass of solution is found by adding up the mass of the solute and the solvent. Does that make sense to everyone so far? Another way to think about mass percent, another way to think about mass percent can also be phrased in this idea of grams of solute per 100 gram of solution. So gram per 100 gram is a common way of phrasing mass percentage or percent by mass concentrations. So let's look at an example. So in this case, we're asked, what is the percent by mass concentration of sucrose in a solution made by dissolving 7.6 grams of sucrose in 83.4 grams of water? Okay, so we know, let's define what we know. What is our solute? What is our minor component in this case? What is our minor component of this solution? If we have our beaker and we add in 7.6 grams of sucrose, and in addition to that, we're adding an additional amount of water. So in this case, we're also adding 83.4 grams of water. My question to you is, what is the mass of solute? What is the mass of our minor component that is being dissolved? What is the mass of our solute? What does everyone think? What is our solute in this case? What is our minor component of the solution?
Sucrose?
Sucrose, yep. So what is the mass of solute?
7.6.
Yep, exactly right. Okay, so we know the mass of our solute. What about our solvent? What is our major component?
Water.
Yep, and so our mass of solvent would be water, which is 83.4 grams. Perfect. Okay, so then if we want to know the percent by mass, so if we want to know the mass percentage concentration of sucrose, we're going to take the grams of solute, which is 7.6 grams, over the mass of solution, which is the mass of our solute, plus the mass of our solvent, times 100%. Okay, now punching this into our calculator, that gives us, for our mass percentage of sucrose, we have 7.6 divided by, in this case, this simplifies to 7.6 grams divided by 91.0 grams times 100%, which gives us Following sig fig rule, since we only have 2 sig figs, that gives us 8.4%. Does this make sense to everyone? Does this process make sense?
Yes.
Perfect. So let's apply what we've just seen, and let's try to calculate the percent by mass of formaldehyde in a solution made by dissolving 5 grams of formaldehyde in 70 grams of water. So let's work on this example for about 2 to 3 minutes. Don't be shy to share your proposed solutions or proposed problem setups in the chat or verbally, and we'll discuss this example in 2 to 3 minutes. And of course, if you have any questions, don't be shy to ask them verbally or in the chat. So let's try to solve the following example where we're calculating the mass percentage of formaldehyde in this solution. And let's try to get a few more responses in the chat, and then we'll discuss in about another 2 minutes. And it's great to see that we're getting responses in the chat. Let's keep working on this example for another minute to a minute and a half, and we'll discuss momentarily. Okay, so let's discuss this example. So for our grams of solute, what is our solute in this case?
5.0 grams of formaldehyde.
Yep. So our grams of solute, we have 5.0 grams of formaldehyde. Okay, and what about our solvent? What is our solvent in this case? What is our major component of the solution? Yep, so we have 70.0 grams of water. Okay, so if we want to calculate the mass percentage of formaldehyde, all we have to do is take the grams of solute over the total mass of the solution, which is the grams of solute plus the grams of solvent. So punching this into our calculator, that in turn gives us 6.7% following sig fig rules. And this is the mass percentage of formaldehyde in this solution. You have to be specific what your mass percentage is referring to. In this case, we're looking at the mass percentage of our solute, which is formaldehyde. Does that make sense to everyone? Does that idea make sense to everyone?
Professor, how did you get 6.7 like that?
Because when we take 5 over 75, you get as a raw number output from your calculator, you get 6.66. Now, since our inputs have 2 sig figs, we have to round our input to 2 significant figures. Does that make sense?
Okay, thank you.
Perfect. So let's keep going now. And let's look at another example where we're asked how many grams of sucrose must be added to 375 grams of water to prepare a 2.75% mass over mass solution. Okay. So the first thing that we have to do is we'll write out our equation. So we know that the mass percentage of sucrose, which we're given in the problem, is 2.75%, is equal to the grams of sucrose over the grams of sucrose plus the grams of water times 100%. Okay, that's what we know. And we also know that the grams of water, what is our mass of water in this case?
375.
Yep, so we have 375 grams of water. So plugging this in, we see that our mass percentage, which is 2.75%, is equal to the grams of sucrose over the grams of sucrose plus the grams of water times 100%. And we can plug in for the grams of water, our 375 grams. Okay. And now all we have to do is solve algebraically. So first things first, we can divide both sides by 100. And that clears up our 100%. So that in turn gives us 0.0275 is equal to the grams of sucrose over the grams of sucrose plus 375 grams. So now what we're going to do is we're going to move this term to the left via multiplication. So we have 0.0275 times the grams of sucrose plus 375 grams is equal to the grams of sucrose. Okay, so we can distribute this term. We can just as easily distribute this term. And that gives us 0.0275 times the grams of sucrose plus, so we have 375 times 0.375 times 0.0275. Punching that into our calculator, that gives us 10.3125, and that is equal to the grams of sucrose. So next what we're going to do is we're going to subtract and we're going to move this sucrose term. So in this case, we have 1 minus 0.0275 times the grams of sucrose is equal to 10.3125 grams. Okay, so now all we have to do then to solve for the grams of sucrose is resolve this expression. So we have 10.3125 grams divided by, let me draw this a little bit higher. So we have 10.3125 grams over 1 minus 0.0275. So punching this into our calculator, that in turn gives us 10.6 grams of sucrose, respecting the fact that our mass percentage and initial input had 3 significant figures. Does this process make sense? Once we get to the setup, the rest is just algebra. I just wanted to show the algebra explicitly so that way you understand how to go about isolating and solving for your desired variable. So in turn, we write out what we know, we plug in all of our known information, and then we solve for our desired quantity. The 1 came from the fact that if there is no explicit number written in front of the grams of sucrose, it's implied that a 1 is present.
Professor, how do you get the 10.6?
Could you repeat that, please?
How did you get the 10.6 grams?
So once we've isolated out for the grams of sucrose, we first got this 10.3125 by multiplying our mass percentage over 100 by the mass of our solvent. So we took 0.0275 times 375, and that gives us 10.3125. Okay? Once we've solved for this term to isolate and get the grams of sucrose, we then divide by this 1 minus 0.0275 term. So we hit the division symbol and then parentheses 1 minus 0.0275. And at the end, when you punch this into your calculator, you'll get the raw value of 10.604 grams that you round to 3 sig figs. Does that answer your question?
Yes, thank you.
Perfect. Any other questions on this representative example? Okay then, so let's try to apply what we've learned, and I'd like you to tell me how many grams of sodium chloride are present in 300 grams of a 5% mass over mass solution of sodium chloride in water. So just like the previous problem, you're going to write out your known quantities, and then you're going to solve for the unknown quantity. So let's work on this example for about 2 to 3 minutes, and then we'll discuss. And it's great to see the responses that we're getting in the chat. Let's try to get a few more responses before we discuss in about 2 minutes. And of course, if you have any questions, don't be shy to ask them in the chat or verbally, and I'd be happy to get your questions addressed. So let's keep working on this example. I'd like to see a few more responses in the chat or questions in the chat or verbally. and we'll discuss in about another 1 to 2 minutes. And it's great to see a range of responses in the chat. Let's keep working on this example and we'll discuss in about another minute. And if there are any questions, don't be shy to ask. Okay, so let's look at this example. So we're asked how many grams of sodium chloride are present in 300 grams of a 5% mass over mass solution. So we know the mass percentage of sodium chloride is 5.0%. And that's equal to the grams of sodium chloride over the total grams of solution times 100%. And we know from the problem that the grams of solution are equal to 300 grams. Therefore, substituting, we get 5.0% is equal to the grams of sodium chloride over 300 grams times 100%. So then the grams of sodium chloride are equal to 5 over 100 times 300 grams, which in turn gives us the grams of sodium chloride are equal to 15 grams. Because we only have one sig fig here, we have to round up, and that gives us 20 grams. Does this question make sense for everyone? Does this question make sense?
Yes.
Perfect, perfect. So let's keep going now. And let's try to solve the following question. We're asked how many grams of sodium hydroxide must be added to 250 grams of water to prepare a 3% mass over mass solution of sodium hydroxide. Oh, the reason why it's not sucrose is because looking at the solution is explicitly defined as a solution of sodium chloride. So the grams of solute depends on the type of solution that you're dealing with. In this case, because it's a solution of sodium chloride, our solute is sodium chloride. To answer the question in the chat, does that make sense? Okay, so let's take a look at this example where we're preparing a 3% mass over mass solution of sodium hydroxide. This time we're asked how many grams of solute, sodium hydroxide, must be added to our solvent, water, to make a 3% mass over mass solution. So let's get started with this example. And if you have any questions or proposed responses, don't be shy to share it in the chat or verbally. And it's great to see that we're already getting some responses in the chat. Let's try to get a few more responses before we discuss in about another 2 to 3 minutes. And let's try to get a few more responses or questions in the chat, and then we'll discuss in about another 1 to 2 minutes. And it's great to see a range of responses in the chat, and we'll discuss in about another minute. Don't be shy to ask a question as well in the chat or verbally as you work through these problems. Okay, so let's take a look at this example. So we know that the mass percentage of sodium hydroxide is equal to the grams of sodium hydroxide over the grams of sodium hydroxide plus the grams of water, where sodium hydroxide is our solute and water is our solvent. Okay, so we know the mass percentage is 3.00%. We also know that our grams of water, which is our solvent, are equal to 250 grams. Ergo, our mass percentage, which is equal to 3.00%, is equal to the grams of sodium hydroxide over the grams of sodium hydroxide plus 250 grams times 100%. Okay, now that we have this set up, we're going to solve, and we get 3.00 over 100 times the grams of sodium hydroxide plus 250 grams is equal to the grams of sodium hydroxide. Ergo, 250 grams times 3.00 over 100 is equal to 1.00 minus 3.00 over 100 times the grams of sodium hydroxide. Finishing off this expression, our grams of sodium hydroxide are equal to 250 grams. I'm going to multiply this term out just to make it easier to see. So we have 250 times 3 over 100. So our grams of sodium hydroxide are equal to 7.5 grams divided by 1 minus 3 over 100, which is 0.97. Punching that into our calculator, we have 7.5 over 0.97, and that gives us 7.7 grams. Perfect. Why do we report 2 sig figs? Our least precise input measurement has 2 sig figs. Does this example make sense to everyone? Does this example make sense?
Yes.
Perfect. So then, let's do one more example to showcase another type of calculation. I'd like you to tell me what mass of lithium carbonate is present in 150 grams of a 2.5% mass or mass solution of lithium carbonate in water. It seems students are getting faster at these calculations. That's okay. Let's take about 2 to 3 minutes to work through this example, and then we'll discuss as a group. Don't be shy to submit your proposed responses. Don't be shy to submit your proposed responses verbally or in the chat, and I'd be happy to provide feedback. And if you have any questions or if you have a proposed response for this problem, don't be shy to submit it in the chat or ask a question or share your responses verbally. Keep in mind that the best way to approach these problems is to write what you know and then solve for what you don't know. And we'll discuss this example in about another 1 to 2 minutes. Let's try to get a few more responses before we discuss. And if you have any questions, don't be shy to ask. And we'll discuss in another minute. Don't be shy if you have any questions to ask them in the chat or verbally. These are very common formulation problems that you may encounter in terms of preparing solutions. Okay, so let's discuss. So we know that the mass percentage, which is 2.5%, is equal to the grams of lithium carbonate over the grams of solution times 100%. And we know that the grams of our solution, which includes our solute and our solvent, is equal to 150 grams. So then, substituting, we have 2.5% is equal to the grams of lithium carbonate over 150 grams times 100%. So then the grams of lithium carbonate are equal to 2.5 over 100% times 150 grams. Okay, and that gives us a grams of lithium carbonate equal to 2.5 times 150 over 100. That gives us 3.75 grams that we round to 2 sig figs, which gives us 3.8 grams. Does this question make sense to everyone?
Yes.
Perfect. Okay, so let's keep going now and let's look at a relative to mass percent, which is volume percent. This is commonly used when you have a solute that is a liquid at room temperature. So volume percent looks very similar to mass percent, but you have to remember that we're dealing with units of volume. So volume percent is defined as the volume of solute over the volume of solution. Again, volume percent or percent by volume is unitless. Now, just like before, the total volume of the solution is the volume of the solute plus the solvent. Volume percent can also be thought of as the milliliters of solute per 100 milliliters of solution. So let's look at an example. In this case, we're asked how many milliliters of ethanol are needed to make 2.35 liters of a 25.6% volume over volume ethanol solution. Okay, so let's just write what we know. So we know that the volume percent of ethanol, because that's our solute in this case, the volume percent of ethanol, which is equal to 25.6%, is equal to the milliliters of ethanol over and in this case, since we know the total volume and the total volumes in liters, let's write it as the liters of ethanol over the liters of solution times 100%. That in turn gives us 25.6% is equal to the liters of ethanol over 2.35 liters times 100%. So then we get, after solving, that the liters of ethanol are equal to 25.6% over 100% times 2.35 liters, which in turn gives us 25.6 over 100 times 2.35, which gives us 0.6016 liters. And keep in mind, the question is asking for the volume in milliliters, so we need to convert. So in 1 milliliter, there are 10 to the negative third liter. So that in turn gives us 602 milliliters. Why do we have 3 sig figs? Both of our inputs have 3 sig figs. So this is solved very similarly to how we solved a mass percentage problem. The only difference is now that we're dealing with units of volume, we have to be particularly attentive to what units we are given in the problem. Does that idea make sense to everyone?
Yes.
Perfect. So let's test what we've just learned and let's apply what we've just learned. And I'd like you to answer the following question. How many milliliters of acetic acid are needed to make 1.50 liters of a 6% volume over volume acetic acid solution? And we will discuss this example in about 2 to 3 minutes. And I'd like to see some questions and responses shared in the chat or verbally.
Professor, can you scroll down just a little bit? I can't see one number out there. I mean, the other way, sorry. There, thank you.
And don't be shy to share your responses in the chat or verbally. And we'll discuss in about another 1.5 to 2 minutes. And don't be shy to share your responses or questions in the chat or verbally, and we'll discuss in about another minute. I'd like to see a few more responses, just so that way I can get a sense of how the class is approaching and progressing through these problems. Okay, so let's talk about this example. Let's talk through this example. So in this case, we're asked to figure out what volume of acetic acid in milliliters, keep that in mind, are needed to make 1.50 liters of a 6% volume over volume solution. Okay, so we know that for our volume percent, in this case, we're looking at the volume percent of acetic acid, which is equal to 6.00%. That gives us the liters of acetic acid over the total volume in liters of solution times 100%. And we know the liters of our solution is 1.50 liters. So then the liters of acetic acid are equal to 6.00% over 100 times the volume of solution, which is 1.50 liters. Punching that into our calculator, that in turn gives us 0.090 liters. Oh, 9000, sorry about that. And then we know that in 1 milliliter, there are 10 to the negative third liter. So punching that in, that gives us a final volume of 9.00 milliliters. Oops, 90.0 milliliters of acetic acid. Perfect. Any questions on this example? Any questions on this example? Okay, so let's look at another version of a volume percent question. And I'll showcase the first example and you'll work on a related example. So in this case, we're asked what volume of water is needed to prepare a 15% volume over volume solution of ethanol containing 5 milliliters of ethanol. Okay, so let's write out what we know. So the volume percentage of ethanol is equal to the milliliters of ethanol over the milliliters of ethanol plus the milliliters of water. That's our total volume of solution times 100%. And we know that the milliliters of ethanol, which is our solute, is 5.0 milliliters. Okay, and we also know that our volume percent is 15.0%. So then, substituting, we have 15.0% is equal to 5.0 milliliters over 5.0 milliliters plus the milliliters of water. So then, solving for the volume of water, we get 15.0% times 5.0 milliliters plus the milliliters of water is equal to 5.0 milliliters times 100%. So solving 15.0% times the milliliters of water is equal to 5.0 milliliters times 100% minus 15.0% times 5.0 milliliters. This is just algebraically solving out for our desired term. That in turn gives us the milliliters of water as 5.0 milliliters times 100% minus 15.0% times 5.0 mils over 15.0%. So if we punch this into our calculator, so we have 5 times 100 minus 15 times 5 over 15, and that gives us a volume of water of 28.3 milliliters that we round to 28 milliliters of water. Does this example make sense to everyone?
Yes.
Perfect. So then, let's look and let's apply what we've learned to the following example. In this case, we're asked what volume of water is needed to prepare a 10.6% volume over volume solution of acetone containing 10 milliliters of acetone. So let's work on this example for about 2 to 3 minutes, and then we'll discuss. Perfect. Okay, so let's take a look at this next problem. Let's try to solve the following volume over volume percent calculation. So let's work on this example for about 2 to 3 minutes, and we'll discuss momentarily. Don't be shy to share your questions and responses in the chat or verbally. And of course, if you have any questions or proposed responses, don't be shy to share it in the chat or verbally. And let's keep working on this example, and don't be shy to share your responses in the chat or verbally, just so that way I can get a sense that everyone's comfortable with the material. And I would double check your order of magnitude and double check the units for the volume of acetone as well. And if you could report your final answers with units, that would greatly help. Perfect. So let's try to get a few more responses in the chat or verbally. and then we'll discuss in about another 1.5 to 2 minutes. Student wants me to scroll up. This was the previous question that we covered. Okay, let's spend about another minute. I'd like to see a response from at least another 1 to 2 members of the class. Let's try to get a few more responses in the chat, and then we'll discuss momentarily in about another minute.
What is V divided by V?
That is representing volume over volume.
Okay, thank you.
Mhm. So let's talk about this example. So we know our volume percent. In this case, we're looking at the volume percentage of acetone because we're told acetone is our solute. That is equal to the volume of acetone over the volume of acetone plus the volume of water times 100%. And we know the volume percent is 10.6%. We also know that the volume of acetone, which is our solute, is 10 milliliters. So substituting, our volume percent is equal to the volume of acetone over the volume of acetone plus the volume of water times 100%. Keep in mind our units of volume are in milliliters currently. So we have 10.6% times 10 milliliters plus the volume of water is equal to 10 milliliters times 100%. So then we know that 10.6 times the volume of water is equal to 10 milliliters times 100% minus 10.6% times 10 mils. Okay. We also know then that the volume of water is equal to 10 mils times 100% minus 10.6% times 10 mils over 10.6. Okay, so plugging this into our calculator now, we're still in units of milliliters. So that gives us 10 times 100 minus 10.6 times 10 over 10.6. And that gives us a volume of water of 84.3 mils that we round to 80 milliliters because we're stuck with one significant figure. Notice the trailing zero is not significant and it's just serving as a placeholder. Well, yes. Yeah, the percentage indicator doesn't, I mean, I guess you can phrase it as the percentage indicator isn't modifying the number in this case.
Well,
So
it does for mine. Like I got 0.843, but
oh,
that's because I'm
are you entering in the percentage in your
Yeah.
calculator? Oh, okay. So what's important to note is that any of these numbers entered, the percentage doesn't actually get entered into your calculator. Because
Oh.
when you enter the percentage function in your calculator, what you're essentially doing is you're
Multiplying by 0.10
oh
or
well
point.
you're depending on how your calculator is set up, when you hit the percentage function, it is likely setting it up so that it's multiplying or dividing by 100 to convert the number into a percentage over 100.
Okay.
So when you're entering this into your calculator, don't enter any of these percentages. They're just held as placeholders because our original quantities were written as percentages.
Okay. That makes sense. Thank you.
Perfect. Perfect. Any other questions on this example? Okay.
Professor, so when we multiply like the volume, the water volume, like the 10 mLs,
Yeah.
we don't enter the percentage, we just multiply it by 100
Yep, exactly.
and then subtract the other two.
Yep, exactly.
Okay, thank you.
Perfect. So let's keep going now. And let's look at the next major expression in terms of concentration, which is mass over volume percent. Mass over volume percent is defined as the mass of solute over the volume of solution. It has units of gram per milliliter. That's important. So mass over volume percent can be thought of as the grams of solute per 100 milliliters of solution. So let's look at an example. A normal saline solution is often a 0.92% mass over volume solution of sodium chloride in water. And we're asked how many grams of sodium chloride are required to prepare 35 milliliters of saline solution. Okay, so we know our mass over volume percentage. In this case, this is the mass over volume percentage of sodium chloride. It's equal to the grams of sodium chloride over the volume of solution times 100%. And we know our mass over volume percent is 0.92%. We also know our volume of solution is 35.0 milliliters. So then our mass over volume percent, excuse me. So our mass over volume percent, which is equal to 0.92%, is equal to the grams of sodium chloride over the volume of solution in milliliters, which is 35 milliliters, times 100%. So then the grams of sodium chloride are equal to 0.92% times 35.0 milliliters over 100%. And punching this into the calculator, that in turn gives us 0.32 grams of sodium chloride. Does this question make sense to everyone? Any question on this example? Okay, let's then apply what we've learned and let's work on the following example. In this case, we're given that sodium methoxide is sold as a 30% mass over volume solution, and we're asked how many grams of sodium methoxide are required to prepare 250 milliliters of a 30% mass over volume sodium methoxide solution. Okay, so Let's work on this example over the course of 2 to 3 minutes. And if you have any questions or proposed responses, don't be shy to share them in the chat or verbally. Let's try to get a few more responses or questions in the chat. And then we'll discuss this example in another minute to a minute and a half. Okay, so let's discuss this example. So we know that the mass over volume percent of sodium methoxide is equal to the grams of sodium methoxide over the milliliters of solution times 100%. We know that the volume of our solution is 250.0 mils. Okay, and we know our mass over volume percent is 30.0%. As a result then, from these pieces of information, we know that we can solve for the mass of sodium methoxide. So our grams of sodium methoxide over our milliliters of solution times 100%, and we know that our grams of methoxide are equal to 30.0 over 100% times 250.0 milliliters. And that gives us for our grams of methoxide. So we have 30 over 100 times 250. And that in turn gives us 75.0 grams. Does this question make sense to everyone so far? Does this make sense to everyone so far? Perfect. So let's keep going with this. And now let's talk about probably the most chemically relevant measure of concentration, molarity. Now it's very important to pay attention to the units in molarity. Molarity describes the moles of solute per liter of solution. So molarity represents concentration in terms of mole per liter. So molarity, which is written with a large M, represents the concentration in mole per liter, mole solute per liter solution. So the total volume of the solution. Now, if you need to know the volume of a solution that you need to add, we can rearrange this equation to get the volume of solution is equal to the moles of solute needed over the molarity. Okay, now a shorthand way of writing concentration is to put a bracket around the compound formula. So for example, the molarity of sodium ions would be written as sodium plus in brackets. So anytime you see these brackets, that's a sign of concentration, and more specifically, a sign that you're referring to molarity. Does that make sense to everyone so far? Does that make sense to everyone so far? Okay, one thing I do want you to note is that because molarity is a metric unit, we can apply prefixes. So if you apply a prefix in front of molarity, it modifies your unit. So for example, this unit combination represents millimolar, which is millimoles per liter. You may see this come up a lot in biological settings or for solution prep where you're dealing with pretty active solute components. So just note, because this is a metric unit, it can be modified with prefixes. Nothing that we haven't seen before. Okay, so let's practice some calculations here. I'll do the first and you'll follow up with the second. So in this case, you're asked to determine the molarity of a solution obtained from 4.35 moles of potassium permanganate dissolved in enough water to make 750 milliliters of solution. Okay, now this is where you have to be careful with the units. So the molarity of potassium permanganate is defined as the moles of potassium permanganate over the total volume in liters of the solution. So then if we have 750 milliliters, we're going to need to convert this to liters. And we know there are 10 to the negative third liters in 1 milliliter. So that gives us 0.75 liters of solution. Now that we have everything in the correct units, we can solve for the molarity of permanganate, which is 4.35 moles of potassium permanganate over 0.75 liters. And that in turn gives us, following sig fig rules, our final output should have 2 sig figs, and that gives us 5.8 moles of potassium permanganate per 1 liter, or 5.8 molar KMnO4. You have to specify what you're referring to when you indicate molarity. This is the molarity, the concentration of potassium permanganate. You have to be specific because, as we'll see later on, you may want to calculate the concentration of a certain species in solution. And if you aren't specific, you're going to get things mixed up. Does this framework make sense? Does this make sense for calculating molarity? Okay, so if we're comfortable with this example, let's move on and let's try to tackle the following. So in this case, I'd like you to determine the molarity of a solution when 10 moles of sodium hydroxide are dissolved in enough water to make a 1.50 liter solution. So let's work on this example for about 2 minutes. Let's try to see some responses in the chat or verbally, and then we'll discuss momentarily. And it's great to see the range of responses in the chat. Let's give students about another 30 seconds to a minute to complete their calculations, and then we'll discuss as a class. Okay, so let's discuss this example. So in this case, we know that the molarity of sodium hydroxide is equal to the moles of sodium hydroxide over the liters of solution. So if we have 10.0 moles of sodium hydroxide and 1.50 liters of solution, punching this in, we get 10 over 1.50, which gives us 6.67 moles of sodium hydroxide per 1 liter, or the molarity of sodium hydroxide is equal to 6.67 molar. Does this question make sense to everyone so far? Okay, so let's keep going now and let's showcase an alternative set of calculations that you may have to do. In this case, we're asked to calculate the mass of solute dissolved in 2.5 liters of a 0.25 molar aqueous solution of copper 2 sulfate. Okay, so we know that molarity can be thought of as a conversion factor. So molarity serves as a bridge that allows us to convert between the volume in liters and the moles of solute. Okay, we know this. We've seen this before. Now, of course, we know that once we have the moles of solute, we can just as easily use all of our other mass to mole conversions that we've learned to get the grams of solute, right? We can go from moles to grams. And the way that we do that is using what conversion factor? What gets us between grams and moles? What conversion factor? Molar mass, exactly right. Okay, so now that we have our solution map established, keeping in mind that molarity is just another conversion factor, if we have 2.5 liters of solution, looking at molarity, looking at molarity, we know that we have 0.25 moles of copper 2 sulfate in 1 liter. Okay. So we're now in moles of copper 2 sulfate. And then for grams, we know that we have 159.61 gram for every mole of copper sulfate. All we have to do now is punch this into our calculator. We have 2.5 times 0.25 times 159.61, and that in turn gives us so we have 0.25 times 2.5 times 159.61, and that in turn gives us 99.7 grams that we round to 1.0 times 10 to the second grams to respect the fact that both of our inputs have 2 sig figs. Does that make sense to everyone? Okay, so let's keep going now. And let's look at the following example where we're asked how many grams of sucrose are present in 185 milliliters of 2.50 molar sucrose solution. So let's take about 2 to 3 minutes to work on the following example, and then we'll discuss as a class. Don't be shy to submit your responses in the chat or verbally, or ask a question. I saw in the chat there was a question, why is this not 98? Well, because 7 is greater than 5, we'd round up. And the next digit would be 100. And in order to write 100 with 2 sig figs, it would be 1.0 times 10 to the second. Does that make sense? Okay, perfect. So let's apply what we've learned on the instructor example to the following problem. And let's try to submit some responses or questions in the chat, and then we'll discuss. And because molarity has units of mole per liter, yes, you will have to end up converting the volume from milliliters to liters. So let's keep working on this example, and we'll discuss in about another 2 minutes. Don't be shy to share any questions or responses that you have in the chat. And it's great to see a range of student responses. So as we have a fair number of student responses, let's discuss this question. So the first thing that we're going to do is we're going to make a solution map. So we know we have the milliliters of solution, and we're going to have to convert to liters. If our final goal is to get the grams of sucrose, then it's logical then to get the grams from the moles of sucrose. And to get the moles of sucrose, we can get that using the volume and the molarity. So filling in the conversion factors that we need, we first need the molarity to go from the volume in liters to the moles of solute, and then we need our molar mass to go from the moles to the grams. Okay, so now that we have that set up, let's make these different colors so that way it's clear. So for our molar mass, for C12H22O11, we have 12 times 12 plus 1 times 22 plus 16 times 11. And that in turn gives us a molar mass of 342 gram per mole. Okay, perfect. Now we're ready to continue on with this. So if we have 185 milliliters, we know that we have 10 to the negative third liter per mil. For our molarity, we know that we have 2.50 moles of sucrose per liter. And then we know to get the mass, we have 342 grams per mole of sucrose. Okay, so punching this into our calculator, we have 185 times 10 to the negative second times 2.5 times 342. And that in turn gives us 158 grams. Does this question make sense to everyone? Any questions on this example? If not, let's keep going on this and let's look at another variation. So in this case, we're given that a student wants to prepare a 0.15 molar solution of potassium hydroxide in water. If the student starts with 40 grams of potassium hydroxide, what total volume of solution should the student prepare? Okay, so we're given the grams of potassium hydroxide, and at the end, we want to get the liters of solution. Now we can get the liters of solution from the moles of potassium hydroxide if we know the molarity. We also know that we can go from grams of potassium hydroxide to moles using our molar mass. Okay, so then let's look at the molar mass. So we know the molar mass of potassium hydroxide. So potassium is 39.9 gram per mole. Oxygen is 16 gram per mole. Hydrogen is 1 gram per mole. So that gives us 39.9 plus 16 plus 1, 56.9 gram per mole. Okay. So then, if we have 40.0 grams of potassium hydroxide, we know that in 1 mole of potassium hydroxide, we have 56.9 grams. And now to go from moles to liters, we know that in 1 liter of solution, based on our molarity, we have 0.15 moles of potassium hydroxide. So punching that into our calculator, we have 40 over 56.9 divided by 0.15, and that in turn gives us 4.7 liters of solution. Does this example make sense to everyone? Does this example make sense? Any questions on this example? Okay, then let's apply what we've learned to the following example. And let's work on this example for about 3 minutes. And let's figure out what total volume of solution needs to be prepared if you're trying to prepare a 0.45 molar solution of copper chloride from 50 grams of copper chloride. And don't be shy to share any questions or responses that you have in the chat. And let's try to get a few more questions and responses in the chat, and we'll discuss in about 2 minutes. And it's great to see the range of student responses that we have so far. Let's spend about another minute on this problem. And if there are any other questions that we can address before we tackle this problem as a group, don't be shy to let me know. Okay, so let's discuss this example. So in this case, we are given the grams of copper chloride, okay? And our end goal is to get the liters of solution. Again, as always, we can get the liters of solution from the moles of solute, in this case, copper chloride. In order to accomplish this conversion, to go from grams of copper chloride to moles of copper chloride, we'll need our molar mass. And to go from the moles of solute to the liters of solution, we'll need our molarity. Now, for our molar mass of copper chloride, we're going to need to go to the periodic table. And for copper, we have 63.54 gram per mole. Chlorine, we have 35.45 gram per mole. And we know that we have 2 chlorine atoms. So punching this into our calculator, we have 63.54 plus 35.45 times 2 plus 63.54. And that gives us a molar mass of 197.98 gram per mole. Okay, so now we have all the tools we need to execute on this problem. So starting off with 50.0 grams of copper chloride, we know from this, we know in 1 mole of copper chloride, we have 197.98 grams. Additionally, we know that in 1 liter of solution, we have 0.45 moles of copper chloride. So punching this in, we have 50 over 197.98 divided by 0.45, and that gives us 0.56 liters. Does this example make sense to everyone?
I think probably you calculated the molar mass copper.
Yeah.
Long.
I see I went through and checked. Yeah, it's 134. Sorry about that. Something ended up getting stored. I was wondering why the numbers were off compared to the student response. So let's punch that in one more time. Yep, so that gives us at the end, we get out 0.82 liters. Perfect. Any questions on this example?
Professor, how do you get the 63.54 gram?
These are the molar masses of copper and chlorine respectively. And by adding up the total mass of all of the atoms in copper chloride, that gives you your molar mass of copper chloride.
Okay.
And all of these masses are obtained from the periodic table.
Okay, got it. Thank you.
Perfect. So this is a great stopping point for today. Everything up to today, you'll be responsible for on the exam. And if there's any topic that we cover Wednesday that I've included on the exam, I'll let you know. But this is the bulk of the type of questions that you will see for solutions as part of exam 2. The practice exam will be up on Wednesday, and we'll be doing a review of our practice exam for exam 2 on Wednesday. so that way you can take and complete the formal exam by Sunday. So it was great seeing students engage in problem solving for all of these examples. You'll see similar versions of these questions or variants on these questions on your exam. In terms of what else is due this week, the only thing that's due this week is the exam. That's the only thing. We'll be starting a lab this week, but the lab will be due next Sunday as following convention. So with that,